So this presentation is related to a lot of work that has been done around WebRTC and SignalWire, in particular for the troubleshooting phase that becomes more important and gives confidence for users and developers around its usage. So about me, I started a long time ago in VoIP, around 2001. I've been in TrueCon, and in fact, in 2014 at ClueCon, I was presenting one of the first integrations with Camaillo and FreeSwitch for WebRTC, with using SIP as signaling. Then other relevance in 2019, POC with FreeSwitch working with Janus for heterogeneous integration between MCU and SFU. In 2022, still working WebRTC in SignalWire with moving and testing at scale WebRTC applications. And a slightly different version of this presentation this spring in Berlin at Camaillo World. So the goals of this presentation is somehow to share some common terminology and foster collaboration and provide some tools that could be useful for people that use the SDK for WebRTC sessions. So it will be a little bit of foundations, hopefully not too boring, but I think technically it could be useful to see what's behind the scenes, and then some useful tools for everyday working on it. That can be used at any level, developers or support or customers. A quick demo with some live usage of the tools that I've been presenting. And if there will be enough time, a little bit about typical issues and where to look into using the tools. So in terms of media establishment, you can imagine the simplest possible peer-to-peer negotiation for generating RTP streams. I will focus on audio and video, of course, with WebRTC could be potentially even data channels. The negotiation is a simple offer-answer model using SDP, and the most important aspect is that the RTP streams are always TTLS SRTP encrypted. So there's no, as you probably, maybe people in the audience know most of this information, but so for WebRTC, there isn't a real specification in terms of signaling for negotiation. What's been defined in terms of protocol is the so-called ICE that is managed for exchanging candidates to discover what's the best way to interconnect the media. And ICE uses STAN as a protocol, and in some cases it's possible to use TURN, which uses the STAN protocol, and it's useful for relaying media when necessary. So I think maybe this slide is one of the takeaways for the presentation. I think if this is clear, then everything else in interacting with this any type of troubleshooting will be simpler. So it's the candidate types. So the browser that you can imagine in any NATed or even multiple NATed network has the ability to discover local candidates that are the so-called host candidates, so IP addresses that are directly accessible. And through the help of a STAN server, it can discover what's the IP address and port that it's actually using for going out from the NAT that it's in, which is not directly accessible to the browser. And if it uses a TURN server, then for relaying, it will discover the relay candidate. The relay candidate will be basically allocated in the TURN server. The browser will know about it and will use it in the negotiation of the session. In this case, it's very, very simplified but typical situation when there is a browser behind NAT, free switch available publicly, but also with turn available for relaying media if necessary. And then we have a WebSocket server exchanging signaling between the two, which in fact is, apart from a few details, is exchanging the SDP offer and answer. So, and this one is static. This one is more dynamic, and I think this is maybe even more useful. So very quickly, the WebRTC application, you can imagine the browser, even if it's called or it's calling into the platform, will probably discover the local candidates more quickly than the others. And then it will have the host candidates. Then by talking to the stand server, it will discover the server reflexive candidates. And talking to the turn server, it will discover the relay candidates. So at that point, and I've omitted the turn authentication just for simplifying the diagram. At that point, the browser has an SDP, which is either the offer or the answer, and can send it to the remote party. So this is the other slide that is probably the takeaway from the presentation. So we use turn typically on port 443 because it's a sort of last resort, and typically the last resort is trying to use 443, which is typically open in offices. And we also offer not only UDP but also TCP, because that could be the only possible transport available for that browser in that specific situation. Even if in normal conditions, like for our customers working, for example, in call centers, the networking situation of the browser is not so unpredictable. That's typically something that can be planned. So theoretically, there shouldn't be any need to go over turn using TCP, because that's makes things a little bit more complex, and it requires a little bit more to discover the candidates, because there is an additional round trip for authenticating on turn, and it could add media latency. So STAN is the protocol that it's used for discovering the server reflexive candidates and the relay candidates, but it's also used for monitoring some aspects of the session during the call. Like, for example, with periodic exchanges with the other party, it's possible to estimate the round trip during the call. And even turn, turn theoretically is used only for relaying, but it can be used also as a strategy for doing something like isolating the backend, reducing the number of IP addresses required, or doing something a little bit more clever in terms of putting the turn servers closer to the browsers and optimizing the distance between the browsers and the beginning of our network. And with the ICE transport policy, it's possible on the client side to even decide to go only via turn if needed. It's always a possibility. So in terms of tools, probably nothing too shocking for the community, but I think useful to have around. TCP dump and all the family of these tools, because eventually a network trace will tell you the truth. And Wireshark, for looking into it, Wireshark understands a lot of what's seen on the network with the dissectors, can help you seeing exactly what happened and dissecting and showing you the content of the packets flowing through the network. HEPIC for, as you know, Homer HEPIC for storing important elements during the negotiation or other logs to reconstruct then the calls. This is on the server side. Audacity is a useful tool for editing and looking into audio files. And of course, something that comes together with the WebRTC API is another set of APIs, which is the RTCStats, that can be accessed by the JavaScript application at any time. And they are continuously updated during a session and provide important aspects. And we will see some examples with, so basically RTCStats, it's what's behind Chrome WebRTC internals. And you can dump all those stats into a file and then see later for non-live troubleshooting. We have an internal tools called RTP Insights we use that is capable of looking into, in some cases we collect network traces, and it's able to select the relevant RTP streams and stun interactivity and provide some sort of analysis offline. But also important for any person using the SDK and developing an application on top of it. It's very powerful to have proper console logs and look into the console logs. And it's also possible to see what happens at the WebSocket level. So you just go into the DevTools in Chrome, you look into network, and you will be able to see the interaction between the SDK and the backend. So, as I was mentioning, it's quite different to troubleshoot something that is happening at that moment or something that happened in the past. So these are slightly different approaches. Of course, when possible, it's useful to collect network traces for further analysis in the future. And also when a problem arises for anybody using the browser to save basically a dump of all the WebRTC stats that have been collected so that they can be then used in the future and reanalyzed. And also we saw, maybe it's trivial, but we saw that having recordings available allow the troubleshooter to try to understand by actually even listening to the call when the issues were perceived, and then have important references on the networking side. So even this is quite trivial. So TCP dump, if you have the ability, it's super useful to capture on the browser side, because you will see the interaction visible on locally, and also, if possible, at NAT level. On our side, we do, in some cases, we capture the network activity either at the RTP engine or FreeSwitch sides. That allows us to do analysis, post-analysis, and post-processing for some calls. And this is probably less needed, but potentially, if you are, in this case, if you have your own infrastructure, it may make sense to capture on the turn server side. So Wireshark, as I mentioned, is a free tool, understands a lot of what's happening in the network. It has the concepts of RTP streams. You can have it. You can even tell it, try to interpret everything that you see as UDP. Try to interpret it as if it was RTP, and it does a very good job, because typically Wireshark looks into the SIP signaling and looks into the port and understands which of the UDP packets are RTP based on that. In our case, there's no SIP signaling, but also signaling is encrypted. But with this trick, you can basically tell Wireshark, try to interpret any UDP that you see as an RTP packet. And if the dissector is successful, then you have the RTP. You can see the RTP streams, and we can see it in the demo. It can also play audio with some circumstances, which could be very useful, and can provide, as you can see, the waveform, play the audio for you, and understands the stun protocol. So if you have any doubt about what happened when collecting, say, the server reflexive candidates or the relay candidates, you can most probably just see what happened with Wireshark at the browser side. Of course, it's not for taking notes. I will share the link to the slides, but there are a few filters that can just make it more narrow to see what happened. So you can target specific stun interactivity, like the binding requests and responses, the turn allocations, the authentication at turn level, and even the DTLS establishment. So I mentioned WebRTC internals. It's a tool that is available in Chrome, and it uses the RTCStats API and provides, we will see it in the demo, graphs in a human-friendly way that can be seen and to try to understand what's going on and get an idea of the possible issues. They can be saved, but also it's able to extract the audio that is basically sent to the tab from WebRTC and record the audio files, which will take a lot of space in the disk, but it could be very useful, or even the diagnostics in the packets. So in general, if you are using or will use the SDK, I would definitely recommend try to troubleshooting, getting familiar with WebRTC internals. For, let's say, if Chrome is not your choice, there's something similar in Firefox with about WebRTC, and something analogous in Safari. A little bit hidden in the WebRTC login. So this is a static slide. We will see something in real time. So say you have your WebRTC dump file, which is a collection of all the RTC metrics happen at specific times during the call. You may think about feeding it to an NLM. I saw that it does a good job in understanding if anything went wrong, in particular because it's easy to see, say, for example, the connection state or the ICE connection state, if it's failed or it provides any unusual value. That's probably easy to understand for an LLM. I think the main problem there is providing something that is meaningful for the time frame where the problem happened. So if you leave WebRTC internals running for, say, half an hour, and you have 5 or 6 calls and one was problematic, and you feed everything to the LLM in the same file, it can just struggle and waste your time. So I think, as in any other usage of LLMs, check the conclusions. Don't trust it too much. I saw some cases a little bit too much confidence from humans into what was being provided by ChatGPT, for example. So just to show a little bit of the usage of the Call Fabric SDK, which is the WebRTC SDK currently available. Let's see, maybe just to give you an idea. So first of all, on the client side, when using the SDK, there will be access to the backend to access an authorization token, and that will then will also provide all the information to the client for connecting, like all the details and the ICE servers and so on. And then it's possible to target a specific resource, which is just an address to call. And behind that address, there could be anything. It could be a room, could be phone number, SIP endpoint. It could be a script that you have programmed. It could be a script that connects to another script, and so on. Whatever you may imagine programming. It's quite flexible. Then at that point, it will generate the invite and then get the response from the server side. And of course, once it's online, it can receive calls. So it's completely bidirectional. And then we will see in the demo maybe the media flow in. So let's say if I prepare 5 minutes. So if I prepare Wireshark, I just launch it, and then I launch an application that is based on the CallFabric SDK directory. There is a room for ClueCon. And then, so I open Chrome WebRTC internals on another tab. So first of all, it's interesting to see here that there has been already a collection of the candidates. Like, for example, I have 3 host candidates, 1 server reflexive, and a few relay, even if I'm not actually in any call. This is a strategy we are using recently. It's an attempt to minimize the time to connect the session, and it's particularly useful, say, in a scenario where on the browser side there is an agent and that needs to be connected as quickly as possible to a customer that is already waiting online. So in this way, the SDK is capable of collecting the ICE candidates, already having them available, and practically having an SDP answer or offer ready. The price to pay is a little bit of resources on the turn server side, but so it's a sort of compromise. So Wireshark is running. Then say I place the call. First of all, this is the developer console. So there is the, as I mentioned, console with all the logs, which in this case are quite verbose, could be less verbose. And then in network, you can see the networking activity. And so in case of troubleshooting specific cases, it's super useful to see what was exchanged, the timestamps, and so on. And something that I would recommend, in particular when a problem happens, you can just select this, download the WebRTC internals, becomes just a text file, a small one, less than 1 meg. And then I mentioned earlier the Philippe Anke tool he made available. It's basically an online tool. You can provide a one of those files, and it will do the sort of creation of the graphs for you. So you can see it's not exactly the same as using WebRTC internals, but it's super useful if you are troubleshooting not live, but something that happened in the past. So something interesting, for example, from WebRTC internals. Let's see the graphs. Oh, maybe I should mute myself. The graphs, you can see there is an estimate of the outgoing bit rate, which depends on other elements like packet loss and round trip time. The current round trip time is super important for in cases where there is the perception of delay in the call. In this case, it's just 50 milliseconds, which is very good. And other things, of course, you can see how many bytes were received. This is for the ICE candidate that is in use. And then there is another one, which is the inbound RTP. No, I want to see the remote outbound inbound RTP, say, for audio. This is basically what, in this case, FreeSwitch is providing back to the browser in terms of via the RTCP. So this is an important reference for the browser, because basically it gets from the remote side an understanding of what happens during the traveling of the packets. and it can confirm whether on the receiving side there is, for example, in this case, there was a small number of packets lost, just 13 packets lost, and the round trip is quite constant and small, 50 milliseconds. And all these, if I had saved the file with all this information, would it be also in the file that I exported and then visible again? You can see, for example, visible again in offline with this with FIPO's tool. But I think actually I had a little bit more slides, but I think I'm out of time. Maybe I can benefit from the fact that David is distracted.
You got 2 minutes, Giacomo. 2 minutes? 2 minutes.
Okay, because that says 0. Okay, that's good.
Which are really meant for questions. However, since it's you.
Okay. Right, thank you. So, in fact, in terms of typical issues, I think by experience recently, typical cases are timeout when trying to connect, complaints about high latency. In this case, it's just delay in the audio, hearing silence from one party, or the audio just disappearing during a call, or what they call choppy audio, which is audio that is not quite good and disturbed by clicks or similar cases. So for the timeouts, it's quite easy. It's if there is no possibility to establish the media, then there will be timeouts, and they will be very visible in the network traces. And there will be, for example, the DTLS will just not go up. High latency, I was showing it earlier. The round trip time, super useful. That's a clear indication of problems if that goes too high. And there are two types, candidate pairs and remote inbound RTP. With the RTCStats, it's also possible to see what's the audio energy of the audio incoming. So if the audio energy is low, it's possible that either the track is not connected correctly, if it's completely zero, or it's actually very low what's being received, so which may be confused for silence. And for choppy audio, probably packet loss and jitter and available bandwidth could be problematic. And that's the conclusion. Just wanted to remind the presentation goals, sharing terminology, foster collaboration between you developing with the SDK and your customers and partners, some useful tools to have and use, and that's all.
We only let you roll on, Giacomo, because it's you. You're a special case. Jack has one question. We'll just allow one question before we move on. And after that question, we'll give Giacomo a massive round of applause, but not until he's answered this question from Jack. Here we go.
Giacomo, thank you very much. WebRTC is one of my projects. Are your charts available for sharing, or will they be posted?
Yes.
Okay.
Of course.
So you mentioned the SignalWire SDK as one of your debugging tools. Is there a favorite website that you use for making WebRTC calls? I noticed that there's sometimes people mention try.it.jsip. What's your favorite generic WebRTC test call site?
Okay, so there is, I think it's a useful learning tool. If you search for trickle-eyes, just I'll show you very quickly. So if you search for trickle-eyes, you will find this. Yeah, but
trickle-ice.
Actually, what's useful is this one, WebRTC GitHub.io samples, and then you will find a bunch of very useful examples that go in grow in complexity, like just using get user media or stream capture, RTC peer connection, which is basically what we were discussing, and you will find the working examples for all the cases. And they just use the WebRTC APIs, so it's not any specific implementation.
How about that for a comprehensive answer, Jack? Good one. Listen, I want you all to draw on your maximum appreciation resources to give Giacomo a massive round of applause.